Okay, off we go. Let's see here, and let's see here. I've got to hit this full screen button. Okay, excuse me. So here's where we were last time. We were talking about. Well, let's see here. Let me go back to this screen. So this is kind of a broad framework, sort of a strategy for how we're going to actually cover several really important theorems that are going to be a large part. I don't want to overstate it, but a large part of chapter 6 and 7. By the way, don't forget attendance quiz, attendance code right here. So the big idea is to recognize that once you've established that you have an accumulating quantity, right? Very important that we restrict our attention to accumulating quantities. There we go. That's better. A lot of things follow. It's actually a really useful feature to notice. For one thing, that means it behaves like a physical substance, like a stuff. It might not be a stuff, right? You don't have to view it as a physical stuff, but you may, and I find this to be incredibly useful and incredibly sort of intuitively natural. So I'm going to say we're going to view accumulating quantities. I'm going to encourage y'all strongly to view them as being a physical stuff. Well, once you view it as being a kind of a substance, some sort, well, you can talk about how much substance there is per unit size. You can talk about densities. And densities are what you multiply by sizes to get quantities, right? Again, you're accumulating quantity. And once you know that, then you can compute it with an integral. And again, our standard starter, to me anyway, most intuitively satisfying example is the one I have circled down here. So mass is an accumulating quantity. The whole is the sum of the parts. In any given little piece, mass is mass density times size. Right? So we've done this calculation several times. No big deal. Pretty intuitively satisfied. And the observation we're going to make here is that you can use that same strategy for, again, any accumulating quantity, because you can view it being kind of a stuff. It therefore has an associated, you can think of it that way anyway, density of that stuff per unit size. And therefore, you can compute it with an integral. Totally analogous, even if it's not actually stuff. Okay, so with that in mind, we're going to find a really surprising example of an accumulating quantity that we're going to do all of those things to. And the last thing we did last time was we set up a convention, and this was, look, this is just a convention, and I don't want to go through the details again, but the key point is that going forward, this word boundary is a loaded word. You should always, at least in the context of chapter 6 and 7, and always kind of keep your eye out for this. When you see the word boundary, you should think, oh, that's supposed to be oriented. That word means oriented according to a certain convention. So boundary means oriented. And in this particular context, when you're looking at a two-dimensional region, and you're thinking about specifically the boundary of that two-dimensional region. By the way, notice we use the partial derivative symbol. That's a kind of a shorthand for boundary. A little strange, perhaps, but it is standard convention. It just means boundary. That boundary is oriented according to this convention. You always orient in the direction that puts the region on your left. All right, so again, we talked through the details last time. That's our convention. Okay, so with that established, now here's our surprise accumulating quantity. This is not clear. This is, in fact, not only not intuitive, I would call it counterintuitive. This kind of feels like it shouldn't work. But here it is. If you give me a region, to that region I associate the following quantity, and that is boundary circulation. Claim boundary circulation is an accumulating quantity. The whole is the sum of the parts. Now, let me draw a picture of what I mean by that. Again, keep in mind, accumulation means that you can chop it into pieces And if you compute for the whole versus if you compute on the pieces, the whole is the sum of the parts. So here we've got a large region, sort of the union of these, what I'm calling D1 and D2. And let's write down what do we mean by boundary circulation for that large region. Well, y'all know what a boundary is and y'all know what circulation is. So boundary circulation means we're going to take this region, we're going to look at the boundary curve. Now the boundary curve again follows certain conventions about orientation. We're going to do a vector line integral over that closed boundary curve. Okay, so for the union, this curve that I have in purple is the curve over which we compute the line integral. How are we doing? Is everybody with me so far? I haven't shown anything yet. Right. Let's look at the parts now. Here's the left part. Looking just at D1, let's talk about boundary circulation for D1. Okay, well, D1, I got to think about what is its boundary and how would I compute the circulation along that boundary. Well, here's the boundary of D1. All right, so we would compute the circulation on that green closed curve. And then let's see, we also have D2 over here. How would I represent the boundary circulation for D2? Well, okay, same story. I'm going to look at the boundary. Again, we've got to follow the rules about orientation. Region on the left. There's the curve over which we would compute the vector line integral to get boundary circulation at D2. Now, I've made the claim that the whole is the sum of the parts. It already looks wrong. Right? It's supposed to be that green plus blue is purple. If the whole is the sum of the parts, green plus blue should be purple. There's a bunch of green and blue on this shared sort of edge in the middle, but there's no purple corresponding to that. So this seems wrong, right? On the other hand, let's notice that along in there, the green tracks the purple perfectly. And along in here, the blue tracks the purple perfectly. Likewise, in fact, all the way around the outer edge. So, other than this stuff in the middle, it was working, right? But we have this problem that there's this stuff in the middle, right? There's this shared edge here, the dividing line between D1 and D2, and on the sum of the parts, we've got a couple of line integrals there, but on the whole, looking at the boundary of the whole, there is no such line integral. So what we're looking at here, arguably, is the discrepancy. This is the problem. This is what would seem to make this not an accumulating quantity. Does everybody see the problem? And here's the beautiful thing. That's zero. Our problem is zero because our problem is over a single shared edge, but with opposite orientations. And because they have opposite orientations, that green vector line integral and that blue vector line integral are negatives, and therefore they cancel, and therefore the discrepancy, the problem, is zero. There is no problem. There is no discrepancy. How we doing? Everybody okay with this? So ultimately, the fact that there is this cancellation is, that's what's going to make this all work. That's what makes us have an accumulating quantity. And of course, as we've discussed, hey, the fact of having an accumulating quantity is what's going to allow me to think of it as a stuff, even if it physically isn't. It's going to allow me to think of it as having a density. It's going to allow me to compute the quantity with an integral of that density. All of that is sort of immediate from the fact that discrepancy disappeared. And it's kind of all over but the shouting now. So there's a little bit of, notation that I need to recognize in terminology, and we're basically there, though. So let's get these little sundries out of the way. I do like to point out that, counterintuitive though it is, even if you chop up your region into a million different pieces, this still works. So here's the boundary of the hull, cruising along like that. And I just wanted to zoom in on one portion, but it goes all the way around, boundary of the sort of the union of all of these pieces. And wait a second, when I look at the individual parts, this edge right here, for example, well, there's going to be line integral on that edge. That's not part of the line integral for the hull. So what gives? Well, again, as part of the boundary of that piece, we get line integral oriented that way. As part of the line integral for that piece, boundary line integral for that piece, we get that same red edge oriented that way. And again, that edge appears twice with opposite orientations, and they cancel. Right? So that one cancels. That one cancels. Cancel, 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 cancel. It all just disappears in a puff of smoke. Isn't that wild? So let's take a moment to recognize, how is this possible? How did it work out so conveniently? Well, I feel like we need to give the credit where credit's due. The thing that made it work was this boundary convention. Right? The fact that we have a convention specifically like this, that's what makes it always go like this on shared interior edges and therefore always cancel. Right? So that convention, critical to making this work. Okay. So, like I say, it's all over but the shouting. We have an accumulating quantity, so I can think of it as a physical stuff. It isn't. Cannot emphasize this enough, right? We're looking, for a given region, the quantity that I'm interested in, it's not mass, it's not area, it's not perimeter. Kind of has a little bit of a perimeter feel to it because it does go all the way around, but it's an oriented line integral, right? Anyway, it's one of these quantities, but it's entirely non-physical. It's a vector line integral of whatever vector field. Not physical. And yet it behaves like a substance. This is weird. And since it behaves like a substance, we can talk about its density. And once it has a density, we can compute it with an integral. And pretty much, and let me skip the notation just so we can spike the football here. Here we go. We've got ourselves a quantity. It's not mass. It's not area. It's not population. It's boundary circulation of a given vector field F. Right? That's the quantity. And it is an accumulating quantity. So the whole is the sum of the parts, and I can therefore write it as a Riemann sum of a bunch of little d sigmas. And those little d sigmas stuff is density times size, and we have a density, and here's where I need to go up and talk about our notation, but this is going to be our density curl. And so anyway, this is how we put it together, and this is Green's theorem. It is literally just this argument. Same argument we did for mass, applied to this different accumulating quantity boundary circulation. Okay. All right, so we got to talk about the notation. Let's go ahead and get that done. So keep in mind we are talking about the density that we associate to this new quantity called boundary circulation. As such, we're going to call this circulation density, in recognition that boundary circulation is the quantity in question. I suppose we could call it boundary circulation density, but I think the boundary part is implicit. Various different notations for it. Let's see here. Curl, again, is the most common one. Y'all remember we talked about curl back in chapter 3. I made a an embarrassed assertion with no context, no justification given that, oh yeah, curl, okay, it's a certain formula and it tells you to, in some sense, how much the fluid is kind of rotating. I gave you no context as to why that would be. And we have a pretty good answer for that now. Why is it that curl is a measure of how much the fluid is kind of rotating? Well, because it's literally the density of circulation, and circulation is literally, circulation is literally a measurement of the extent to which the vector field follows along the curve that, of course, goes around. So the extent to which the vector field is doing like the curve is, that's what a vector line integral is the extent to which the fluid is circulating. And thus the extent to which there's a kind of a rotational aspect to the fluid. Is that cool? Everybody happy with that? All right. Okay, so curl, but probably the most common notation here. I also like this one called rot, R-O-T. Looks like rot. That's the problem. I think that's why it's less popular. A little gross. But the motivating base of this is rotation, and arguably from a semantical point of view, kind of more natural. Because, I mean, to me, curl suggests an action. I used the wrong term. Rotation suggests an action. It suggests something that's happening, right? When you see something that's rotating, it's literally moving. To me, curl suggests something static. Like, so, my finger is curled, right? But it's just kind of sitting there, right? And I think the best way to think about what we're actually talking about, the best way to think about circulation is the idea of an action, of something actually rotating. So anyway, that's just an opinion. But anyway, not such a common term, rot, but you probably will see it at some point. And when you do, just keep in mind, rot, it means exactly curl. It's just a different terminology. Let's see here. I like the term Green's operator. And the reason I like the term Green's operator is because it is literally the operator in Green's theorem. If it's the operator in Green's theorem, why wouldn't we call it Green's operator? I don't know. That seems natural to me. So if you say the term Green's operator, people will know what you're talking about, but you probably won't hear other people say that very often. People in most cases just say curl. Motivated by this, let me get back to the right color. Motivated by this, I started using this notation GRN just as an abbreviation of Green's operator. You'll see that on a lot of my old exams. I've kind of abandoned it. I've kind of accepted the reality that I don't get to decide the notations that planet Earth uses, right? And so, oh well. Anyway, so you'll see that on my old exams. Again, it just means curl. Two more that I want to talk about. Get back up to here. This one. Y'all may recall the wedge. This goes back a ways. This goes back to chapter 1. It's one of the last pages in my lecture notes for section 1.4, whichever it is. That's the one about cross products and determinants. So the wedge product is kind of sort of a two-dimensional analog, maybe at best. It's vaguely reminiscent of cross product, but for two-dimensional vectors. It's not a cross product, but it's got some common features. Anyway, as it turns out, the del operator wedge, a two-dimensional vector field P comma Q, happens to give you curl. So isn't that nice? That's a good little exercise to think through to confirm that when you do this, you get this formula. And then lastly, I have to recognize the book uses this expression right here. I am significantly opposed to this expression. This literally uses a cross product. And yet, wait a minute, our vector field is two-dimensional. There is no such thing as a cross product of a two-dimensional vector. Right? So this really bugs me. Now, what they mean when I know exactly what Kali meant when she wrote this, she meant, okay, think of F as being P, comma, Q, comma, 0. Now, okay, I get that, but it remains. That is not what F is. And comma 0 is not the same as plus 0, which really would be the same thing, right? So this, I think, is just fundamentally problematic notation. And don't get me wrong, I would be okay with it if there was a compelling advantage to this notation, and I have not seen it. It works in this, again, if you use the appropriate imagination as to what that cross means, it kind of works, but why that notation is better than just saying curl or wrote, I don't see the win there. So please don't use that notation. Yeah.
What's K in that instance?
It's like IJK. It's the third standard basis vector, E3. Yeah. Okay, so lots of different notations. This is the formula for how to compute it. I'm not going to show y'all why that works. It is mathematically important. But from our point of view, and how is this going to help y'all, right? Is this going to help you gain an intuition for Green's theorem? I don't think so, right? As to, deriving this formula. It's a bunch of details. Needs to be done. I'm glad that it's done. I think we can trust the book on that. If you want to see the computation, you're welcome. It's in the book. But I don't want to spend class time on it. You're not responsible for it. Okay. Let me pause again for questions. Okay, here is Green's theorem. Again, as we've already kind of gone through, Green's theorem says that circulation is an accumulating quantity, and that quantity is computed with an associated density. Again, it's just like every other integral that we've ever computed. The other take is to notice that, that circulation itself is defined with an integral. So you can think of Green's theorem, most people do, as a relationship between a line integral and a double integral. Specifically, a double integral over a two-dimensional region and the corresponding boundary circulation integral on its boundary. So that's kind of interesting that we've got an unexpected relationship between two different integrals, and strangely, two different integrals computed on different domains. This double integral is computed on the interior of D. This integral is computed the boundary of D. Totally different points. Very strange that this works. Everybody with me? All right. We'll come back and talk about these little, the little boilerplate formality, regularity concerns here later. Okay, and we've already talked through this. Okay, let's do an example. Got a good example here. Let's see here. We're being asked to compute an integral, vector line integral. We're given the curve. We are given the vector field. Compute the line integral. Now, the first observation I want to make about this example, you look at the statement of the question there, and nowhere in here, in the statement of the question, does it announce itself as by the way, this is a Green's theorem problem. Hint, use Green's theorem, right? No such suggestion. So it is going to be somewhat on y'all to think about when should I use this tool, right? You do have another tool. Another way you could compute this integral is by parametrizing the curve and then pull back through the parameterization. I could totally do that. Let's think about how undesirable that would be for just a quick second. How would we parameterize the unit circle? Sines and cosines. X and Y are going to be sines and cosines. What happens if you plug in, for X and Y, you plug in sines and cosines in here? You get pretty nasty ugly. I don't want to do it. I'm not saying it couldn't be done. I'm saying I don't want to. Right? Okay, so let's see if we can do this a different way. Vector line integral. Now wait a second. The vector line integral, if I want to use Green's theorem does compute a vector line integral. But very importantly, this does not say you can compute any vector line integral. Very important little detail staring at us right here. This can strictly only be used to compute boundary vector line integrals, which of course are always closed curves and therefore boundary circulations. So it's got to be a boundary. We've already talked about how the fact that this is a boundary is critical to what makes it work, right? If you just say, oh, I'm going to use this to compute whatever random vector line integral, crash and burn. There is no such theorem. So we've got to be very, very careful. We've got to make sure that our curve is a boundary. And now let's think very, very carefully about this. Is my curve a boundary? Well, let's see here. Our curve, again, it's this right here. It's the clockwise oriented unit circle. It's like this, oriented like so. Is that a boundary? No. Close. Not quite. Orientations matter. Right? After all, again, let's just take a moment to recognize the fact that we defined boundary orientation specifically exactly the way we did was what made the cancellation work. Right? You live by the sword, you die by the sword. Right? That we have to follow the rules of what we've set up. So, as indicated here, that domain, that green curve, not a boundary. Everybody okay with that? All right, so you can, of course, read ahead from what I've already got on the page. That curve, not a boundary, but if I just orient it the other way, now it is a boundary. Specifically, now it's the boundary of this disk in here. And so that blue curve, if we had been asked about the blue curve, we would totally be able to use Green's theorem, and that would be no problem. So what we're going to do is we're going to kind of transition the question. We're going to say, well, we were asked about the green integral. The green integral is just a minus sign away from the blue integral, which is a boundary for which I can use Green's theorem, and off we shall go. And so that's the big observation here. We were asked about the integral over C. We are instead going to compute the integral over C minus by inserting a minus sign in recognition of the orientation switch. C minus, as we just observed, is a boundary. And once you recognize that you've got a boundary, you're in business. This boundary line integral is computed by that double integral over the interior. What do you think? Everybody with me? Questions, feel free. Don't forget your minus signs. Carry along, of course. Everybody's good. Alrighty. So, it's all over with shouting. Let's see. We are going to have to compute the curl. The curl of F. Let's see. Our vector field F is this. So I've got to plug in to the curl operator. Now, we've got the curl operator on the previous page. I'll scroll back real quick. Here it is. Curl is this formula right here. It's the x partial of, let me label, it's the x partial of the second coordinate of the vector field minus the y partial of the first coordinate of the vector field. Right? So we like to say dq dx minus dp dy because it rolls off the tongue nicely. But anyway, x partial of the second minus y partial of the first. And keeping that in mind, Easy plug and chug. X partial of the second component is 3. Y partial of the first component is 1. 3 minus 1 is 2. Now we have an integral of a constant 2 over a unit disk. Right? Super simple domain. We don't even have to set this up as an iterated integral. This is a constant. We're just going to have the area times the 2 is the constant factored out. We're done. How we doing? Everybody all right? Okay. Good stuff. Okay, here's another example. This is a weirder example, a little bit weirder. Here, our curve is sort of a sequence of line segments, like this. Ultimately, it's a closed curve. I start and end at the origin, but after doing some weird, kind of a triangular figure 8, if you will, right? And that's my curve over which I want to compute this line integral. And again, the integrand is given. So how am I going to compute that integral? Well, again, option A, our sort of default, brute force direct method would be to parameterize. Pull back through the parameterization. There's 4 separate curves. We would have to do 4 separate integrals. It's all doable, but it's just be a little tedious to have to look at 4 separate parameterizations. Anyway, it's fine, but it's a little tedious. Here's a much better way to do it. The better way to do it is to recognize our curve as 6 curves by taking, if you will, these long edges and reconceiving of them as 2 short edges. And if you do that, then altogether, we've got 6 edges. And check this out. Those together are the boundary of that D1 triangle on the left. Orientations and all. And then what I have on the right, well, oh gosh, it's tempting to say that these 3 blue remaining curves are the boundary of D2, but they're not. They're going the wrong way. And again, orientation is important for this kind of thing. So, but they're all going exactly the wrong way, which means that it is that boundary after you orient everything backwards. In other words, except for that minus sign. What do you think? Everybody good? Feel free to ask. If you're a little uncomfortable, does that make sense to everybody? All right. So, cool. The minus sign here, of course, we can factor out of the integral. That's how you deal with opposite orientations. It gives you an extra minus sign. Now we're looking at, let's see here. Here we go. We're looking at a couple of line integrals. Each one of these is a boundary line integral. This one I can compute with Green's theorem. This one I can compute with Green's theorem. I don't need to worry any longer about the fact that, well, it was actually oriented the wrong way. I've got that minus sign already accounting for that orientation problem. And so this that remains is literally straight up just a boundary line integral. So again, Green's theorem. And so now I've got a couple of double integrals. Now thankfully curl is easy to compute. We've got our vector field here. And the curl of that, well, you take the x partial of the second coordinate minus the y partial of the first coordinate. A couple of little quick calculus derivatives there, and the curl is 9. And so we are, in fact, just looking at the difference of these 2 really easy integrals to compute. And in fact, you don't even need to compute them, because each one of them is 9 times the area of the corresponding triangle. if I can get this, there we go. And you can see that those two triangles pretty evidently have the same areas. So we're looking at something minus itself, answer 0. Everybody all right? All right. Okay, here's a cool application. It is ultimately just Green's theorem. And let me, whoops, wrong color. Let me highlight this first. Here's Green's theorem. Boundary line integral of a vector field, double integral over the interior of the curl, right? That's nothing more than Green's theorem. Now, you will notice it is Green's theorem as applied to a very specific vector field, 0, x. Now, why am I looking at that specific vector field, 0, x? Turns out 0, x has a really nice property. 0, x has the feature easily checked that its curl is 1. And why is that cool? Well, because double integral of curl turns into double integral of 1, which is literally area. Oh, I've already used that color. Literally area. So we have this really surprising result. Just because I chose a special vector field, we have a line integral computing the area of the region that our curve is going around. Right? A boundary line integral computes the area of what's inside of it in this case. Isn't that weird? I think that's super strange. Now you may be thinking to yourself, thanks but no thanks. I'll just use geometry. Geometry is, I feel comfortable with geometry, and all that line integral stuff seems like, way too much machinery for, come on, simple little problems like area. So before you settle on that, let me point out this example that we're going to do, and with lots of details. We'll go through this in just a second. But if the challenge were to compute the area of that monstrosity, sure you want to stick with geometry. Right? That's going to be a really hard area to compute. Now you can break this up into little pieces, right? We could, I could view this as being that triangle plus that, I missed. That triangle plus that triangle plus, that triangle plus that triangle plus that triangle plus that triangle. Here's the problem. Those are mostly not right triangles. And so you've got a horrible task of, you're going to have to drop perpendiculars on, oh my God, it's a nightmare of inconvenience. Right? Everybody see how that's a nightmare? Okay. Let's not. Okay, so we're going to figure out how to use this variation on Green's theorem. Now, real quick, I want to point out that most of the time when you see this written, they rewrite the line integral with coordinate line integral notation. That's all that is. Right? We talked about that coordinate line integral notation last time. It is usually less convenient. In this case, I think I got to hand it to them. I think that is actually more compact and more convenient. Right, so when you see this written down, in most cases you'll see this written down like this. It's just a little bit more efficient to write it down that way. And again, let me remind you, this will happen sometimes, that you will see line integrals written with this coordinate integral notation. Right, and again, heads up, and you got to make sure that you're comfortable with how to sort of interpret one of these as one of those, if as might be needed. Okay. All right. Next observation. When you're talking about a line segment, this line integral is incredibly easy to compute. It's so easy to compute. Now, you got to confirm this formula for yourself. I think is a good little exercise, right? Parameterize a line segment from x1, y1 to x2, y2. write this out from the definition. Go ahead and compute the whole thing, and when you're done, reorganize the terms, blah, blah, blah. You're going to get exactly this. And it's super handy to just remember that the answer is you're going to look at the average value of x over your line segment. You're going to multiply by the change in y over that line segment. Boom. That will always give you the right answer on a straight line segment. So combining this fact and this fact, we are sufficiently armed to do this calculation. We're just going to take these edges one edge at a time. Here's a straight line segment. Right, this is line segment number 1. Let's see, what is the average value of x on that line segment? Well, the average value of x, well, it starts at 1, it ends at 12, and the average halfway in between 1 and 12, 13 halves. There's your x bar. Look how easy that was. Oh my gosh, so simple. Right? All right, what is delta y? Delta y is, let's see, well, y started at 1 and then ended at 6, so delta y is 5. Oh my gosh, so easy. Right? And the formula that we're using says that on that term, on that line segment, we're just going to be, well, I'll do it like this. On that line segment, we just multiply x bar times delta y, and that gives me 65 halves, as it turns out, which, you know, whatever. It's a number. Repeat. All right, now we do have to go around the entire boundary. That's the deal, right? And remember the theorem up here. Got to go around the whole boundary, and it will compute the area for you. So that was term number 1. You got to also do it on the second edge. And then you got to also do it on that third edge. And yada, yada, yada. And of course there's 9 different edges. And yeah, there's a certain amount of arithmetic there. But this arithmetic is, I'm going to go ahead and call this easy arithmetic. Pretty easy arithmetic. And yeah, 9 edges is a lot of edges, but yeah, you can crank this out in 3 minutes, I'll bet, right? No big deal. Answer, done. Not that hard. Is everybody on board? All right. Okay, next application. And this is another one that kind of a little bit surprising. We're going to talk about the idea of flux through a curve. Now, y'all will recall, flashback to chapter 3, we talked about flux through a surface. Right? Flux through a surface represents the total flow rate. If you have a vector field representing the flow of a fluid, and if you want to know volume of fluid per unit time passing through a surface, flux does that calculation for us. That's in 3 dimensions. Here we're going to consider a 2-dimensional fluid. Right? My favorite example is to think about migration patterns of, like, birds or zebras or something like that. Right? And, well, they kind of behave sort of like a fluid. They kind of all tend to go together. And I suppose we could think of them as passing through a surface, but really we tend to talk about things moving on the surface of the earth as passing over curves, like borders. Right? You could imagine that we're keeping track of zebras as they move around, and when do they, for example, cross over the border, let's say, out of a national park, something like that. Right? So anyway, that's just a metaphor, something to think about. Nice exercise I want to encourage y'all to do is that if you are interested in counting the total flow rate of zebras, right? How many zebras per unit time? Here is the 2-dimensional version of flux that computes that. And notice it looks an awful lot like the previous form, the 3-dimensional formula. The 3-dimensional formula was F dot N times the area of the surface. Here it's F dot N times the length of the straight edge curve. Okay, so good exercise. Now again, y'all, the way you're going to do this is you're going to look back to chapter 3. Don't reinvent the wheel. You're going to look back into chapter 3. You're going to find where we did the equivalent calculation in 3 dimensions, and then just kind of adapt it appropriately, and you'll totally get this. Come talk to me if you have any trouble. Come talk to me if you're not sure how to get it set up, you're not sure how to get going. I'm happy to help out, but give it a try. Okay, so related idea. Now keep in mind what we have here is that if you have a finite length straight edge only. Right, so the related idea is, what if I want to look around an entire boundary? And an entire boundary would mean, for example, maybe we look at some two-dimensional region, something like that, and keep in mind boundaries, they'll go around something like that perhaps. And of course boundaries, there's that word boundary. Reflexively, every time you see the word boundary, henceforth you should think, oriented, what's the rule? Oriented in what way? Right? And we've already talked about how along the curve, we always go, I'm going to go ahead and be sloppy about it, counterclockwise, region on the left, better. So, counterclockwise in most cases. But what we need here now is a convention for what do we mean if we're talking about passing through the surface, and the convention is outward. It's an arbitrary convention, again, set up this way to make certain things go kind of conveniently, but it's ultimately arbitrary, and again, planet Earth does it this way, so we're doing it this way. Okay, how we doing, right? So boundary, outward, everybody willing to accept that? Okay. All right, well, we know already that if I look at some little piece of this boundary, some little segment here, some little segment of size ds, we already know the formula for the flux through that little piece. The flux is F dot n times the length, and the length is ds. So on each little piece, it's just F dot n ds. And of course, if you want to add that up over the entire boundary, then you integrate over that entire boundary. Is that cool so far? And here's the problem. I'm sure you've noticed. The problem is we don't know anything about how to compute this kind of an interval. We've never seen this kind of an interval before. We've seen F dot T ds. We have never seen F dot n ds. So what are we supposed to do about that? And there's a wonderful little clever argument here. This is very clever. I wish I'd thought of it. Recalling, we have F, maybe like so. We've got N, outward. And this dot product, F dot N, I'm going to argue that dot product, F dot N. Oh, let's see here. I'll use purple. F dot N. It depends on the lengths of these vectors. It depends on the angle between these vectors. So how about this? Let's take both of these vectors. Let's rotate them both 90 degrees counterclockwise, just because. Right? Rotate them both 9 degrees counterclockwise. That doesn't change their lengths. It doesn't change the angle between them. Therefore, it's not going to change the dot product, right? If I rotate them both by the same amount, the dot product stays the same. But if I do that, rotating them both, check it out, the normal vector becomes the tangent vector. And the what had been F becomes, just the rotation of F, and flashbacks to linear algebra, 90 degrees counterclockwise rotation turns P comma Q into minus Q comma P. Now, we've talked about this at various points in the past. Make sure you're good with this. If you're a little unclear as to why it's minus Q comma P, come talk to me. Happy to help, right? But want to make sure you see how this is a consequence of recognizing that rotations are linear transformations, which we represent with matrices. The columns are the images of standard basis vectors and all that jazz. Okay, so that integral is equal to this integral. Excuse me, that dot product is equal to this dot product. The purple dot product is equal to the yellow dot product. And that allows me to rewrite that with that observation. And now it's kind of all over with the shouting. Let's just finish it up real quick. F perp.tds. Wait a second. TDS is dr. That makes this a good old-fashioned, regular old vector line integral that we have tools for. We totally know how to compute. One of them is we know how to compute it with Green's theorem. After all, it is a boundary line integral. Green's theorem is done by computing curl. Here's the formula for curl. You got to be a little bit careful with this formula for curl. Let me get where I can get this all on the screen here. Yeah, remember the formula for curl is that you take the x partial of the second coordinate. The second coordinate is p. Right? X partial of the second coordinate minus y partial of the first coordinate, which is minus q. You got to be, like I say, a little bit careful about that. And then the minus sign we got two, well, if I can zoom in, here we go. We got two minus signs that sort of cancel, here and here. And that turns into a plus. That makes this, oh my gosh, look at that. We recognize that. That's exactly divergence that we saw back in chapter 3. And so what we have here now is another theorem. This is called the two-dimensional divergence theorem. It's sometimes thought of as a tweak of Green's theorem. I like to think of it as its own separate theorem on its own. If you want to compute the overall outward-oriented boundary flux of a vector field through that boundary curve, double integral over the interior of divergence. We'll do it. And nice example. Oh, I'm over time already. Y'all can take a look at this example. It's very plug and chug, plugging right into that formula. See y'all later. Have a good rest of your Wednesday.